Hello, everyone. Welcome to our talk. Thank you for coming. My co-presenter is Kris Jusiak. He is the author of several libraries that have Boost in the name, but
Ben, please,
we're not ready yet.
1 minute. When I remove overlay, then you will start.
That's right. Sorry, I forgot.
Oh yeah.
All right. Hello, everyone. Thank you for coming to our talk, Just-in-Time Compilation, the next big thing. My co-presenter and colleague is Kris Jusiak. He's the author of several libraries with Boost in the name that aren't quite in Boost. Boost DI for dependency injection, Boost SML for high-performance state machines, and most recently Boost UT or microtest, a single header C++20 testing framework.
And this is Deane. Deane is a great speaker, and Albert the Wizard, a functional programming advocate, one of the very few who actually understand monoids and monads and the meaning of them and know where to find them as well. He has been working on games as well, so if you like playing online games, and you've probably heard of Battle.net, so that's the contribution thanks to Ben. And I've been privileged to work with him at QuantLab for a few past years and really enjoyed it. And you better believe me that you don't want to miss his talk, which is at 1:30 about constructing algorithms.
All right, thanks, Kris. But this talk's about just-in-time compilation. If you saw JF's talk the other day, it's a very sort of complementary talk. JF did a great talk going into the history of JIT. Kris and I are going to talk more about the practicalities of JITting in C++, particularly based on the work that Hal Finkel introduced, which we'll talk about as we go along. So we are going to cover some motivation for JITting. We're going to look at some existing solutions in C++ and other languages. Then we're going to sort of take a deep dive into how it works based on this paper, P1609. Then we're going to riff on some examples, show some examples of things that work today based on this work and things that might work beyond C++20. And then we'll summarize and take a glimpse into the future as we think it might turn out. So why would you want to JIT something? Well, JITting is just-in-time compilation as distinct from ahead-of-time compilation. Ahead-of-time is what we normally think of when we think of compilation. But when we JIT, it's as if we ship the compiler inside the application or library so that we can compile just in time and at the point of need. So yes, we're basically building an application or a library which contains within it Clang in this case, but a compiler that can do JITting, not just when we as developers sit down to write the code, but when our users run the code at install time, at deployment time, or just before runtime. So there are some benefits and drawbacks of JIT compilation. Sometimes ahead of time is not possible if I have things that I don't know ahead of time. Sometimes it's just not desirable because I can achieve better performance with just in time. I can get perf benefits, I can get productivity benefits, and I can just get different workflows and use cases. So if the source is perhaps provided by a client or by a colleague who's using my library application, so an internal client in that sense, or perhaps by a tool that's auto-generating code, obviously, if I don't know it ahead of time, I can't compile it. If I don't have the parameters to constrain the code yet, I can't tailor the code to them at ahead of time compilation. So maybe these arguments are only available at runtime. And if I compile everything ahead of time, it might lock me into an ABI. Whereas if I delay compilation to just at the point of need, just at runtime with JIT, I move to more an API level boundary rather than ABI level boundary. Sometimes this can give performance benefits. So if I'm compiling for just one target, maybe I can achieve the best performance, but many of us are not doing that. Many of us are shipping to multiple architectures and maybe maintaining multiple distributions of the binary for that reason. If we can reduce the amount of binary maintenance we do, that's probably good. And in order to get the best possible optimization, I need the best possible information about all of the code, not just what I know ahead of time. Sometimes it's more productive for me as a programmer. So compilation time is always something we want to minimize, but geoting allows us to make a new trade-off. We're trying to minimize total time. And in the case where you're compiling something and running it, and it might take a long time to run, and you want to compile for the best possible fit to that run, geoting allows you to trade that total time. And sometimes it's actually less expensive in time to JIT something and then run it than to compile something and then ahead of time and then run it. So we get that minimization of the total time rather than just the compilation time versus the user time. And geoting allows us to just compile what's needed and further achieve better productivity for that reason, because we don't have to deal with all use cases if we can tailor the code at the runtime. And then besides that, it just allows different use cases. Many of the things we'll be exploring talk to exactly those use cases. So it's just the tip of the iceberg, really. I liken this to, it's sort of a sea change in development like adopting version control was. And what you're going to see in this talk is, frankly, the stuff we've thought of so far, but I'm sure there's much more to go. So I'll hand over to Kris, and he can take you through some of the existing solutions.
Okay, thank you, Ben. So if you attended JF talk, you probably know that JITing is nothing new. And because of that, there are already a lot of solutions which we will cover. If you haven't attended the JF talk, you definitely should. It's not just in time for the time being, but you should definitely show and go to watch it. So what about the existing solutions? C++ is not new either. So there are a lot of solutions which already exist in C++ for JITing. We'll take a look into a few of them, and we'll focus on one, which we'll dig into way more. So there's a cling, which we'll cover in a second, so I won't be covering it right now. There are runtime compiled C++ and easy JIT, which are leveraging generated code as well as hot reloading of the shared libraries and compiling it under the hood with the GCC or Clang compiler. We won't be covering those. The one which we'll cover here the most is the Clang JIT version of Clang, which is the P1609 version 1 with our custom modifications to it, which we'll take a look into more details. There are also solutions which are more compile time as well, which is demixing is one of them, which we'll briefly take a look, and maybe in the future we'll see how that works. But yeah, there are other solutions as well which we won't cover here. So what's the difference between Cling and Clang JIT? Because that's something which is important to understand, because they are quite popular, Cling especially. Cling is used as a primary, as a read eval print loop or REPL environment, which means that it's based for interaction with the user. So user can, add includes or eval expressions and do things like that. It was primarily built for the researchers at CERN, physicists. On the other hand, Clang JIT is a language extension attribute, which is totally a different approach. It's not REPL, it's just an extension. Cling always compiles the whole program. It's not about, compilation time improvements that much as trying to be able to have the quicker feedback for the researchers and then being able to leverage the out-of-the-box performance provided by C++. On the other hand, JITing with the Clang JIT allows of compilation of specifically annotated functions with its attribute. And because of that, we get a really fast compilation times because we can leverage the memoization of templated functions, which are marked with the Clang JIT attribute. So that gives us much faster compilation times as we go along. Cling is usually not very well optimized, and that's not the main focus on it. It's just the faster iterations. On the other hand, Clang JIT is all about the performance. Its marks optimizations, not even possible at build time, because we can leverage the runtime data and promote it from the from the runtime to the compile time, which we'll take a look in a second. So as I mentioned before, this really exciting and different approach in Deane, which you can actually compile the JIT at compile time. It's similar to what we will be discussing here, therefore we will mention it because it's based on strings, which we'll take a look, have drawbacks and a lot of benefits. But you can see here that in D, that's the language by the way, we have a generate track function, which takes the name and some member and inject a fragment into the code by calling a mixin. So you can think of it like JIT at compile time, extract into your program. So if you run this function with the foo and bar, it will produce a struct foo with the member bar, which is super exciting because you can extend your C++ program as you go. But that's not what we'll be talking about here. We'll be talking about JIT actually at runtime. So let's take a look how it works. Without further ado, let's begin. So just a reminder again that we'll be talking about P1609 and especially about the version 1 because the paper has changed. We also have the modifications to it, which are not open source yet, but they will be in the future. So you can imagine a JIT function which just take a template type T and will print the type ID of it. We'll expect something as mangled name here because standard doesn't specify what the name will be like. But let's take a look when we call it with end. When we call it with type end, we'll just get I, which is the mangled name for an end. Nothing special here, right? We all done that since C++ 98. What about if we add the clang.jit attribute as a follow-up? And we'll have to compile with the fjit. We'll take a look into that. Just a reminder about that. And let's pass instead of the type, kind of a type string, which is a string. So let me just pause here for a second. Just for you to understand, it's like we actually pass in a string here. It's not a type. And what will happen is that this end as a string will be converted by the clang.jit machinery under the hood into the type. So the class T here, the type T, will still be end, and what we will print, it will be the type ID of an end, which will be an I. So yeah, that's the mind-blowing about the clang.jit fact that the runtime here, maybe on this specific example, it's not really runtime yet, might be an end at compile time, but it will produce an end as well from a string. And it also, what is important, the body of the function here, the cout, won't be compiled, won't be even touched until the runtime point of instantiation, which is kind of a bit different concept than usual. It's like, if you don't call it, you don't pay for it. So it won't be even parsed or anything like that. It will be parsed at runtime when you actually call it. And all the flags for the compilation will be passed from the host compilation. So, and they also might be overwritten by your own flags. So that will be exciting. We'll see into that in the future. So I hope that makes sense. So let's take a look into something else. Let's go with this example a bit further. Let's say we have a hello world CPP file in which we actually will JIT the first argument of the command line. Imagine that. We have an argb of 1 being passed to JIT angle brackets. How exciting is that? What will happen when we will when we will compile it AOT style with flags, CXX flags, and fjit? Well, you will notice that the hello world will have 75 megabytes. Well, that's a bit. That's quite a lot for the main, right, with the JIT function. Well, the reason being is the fact that the compiler, the clang compiler, will be included, as well as the precompiled module of the host things. So if you imagine that you have something different, or you have includes and anything before the main, that will be part of the precompiled module, and the compiler, and the compiler will be included as well. So what will happen if you call it? Let's call it with hello world int, and notice here int is being passed from the command line as a string. It will produce an I, which is an int. Double will produce the D, as expected. Default out of the lambda, that will be a C++20 feature, will produce $_0 clang. That's the Mongol name of the unique version of the lambda, which we'll explore way more, so stay tuned. What about if you pass something which won't compile? Well, we'll get a compilation error, and we'll take a look how to handle errors as well. But this error will actually come from the clang compiler itself. So as pointed out before, we can pass the lambdas here. So what about if we actually run the lambda? That will give us an ability to pass basically arbitrary code and do magic things with it. So here we'll pass a lambda which just prints hello world from JIT, and that will be printed with that simple function. We can also leverage the non-type template parameters as well to just simplify the code a bit, but it will produce the same thing. So you can see how exciting is that we can actually leverage the C++ to make modern C++ with lambdas to run basically arbitrary code. Notice here that we cannot do the includes here, so everything like the put, the CSTDO will have to be included from the host side. So handling errors, as we pointed out before, if you pass something which won't compile, what will happen? Well, in this implementation of our clang JIT, we can just get the compilation error exception. So if you did an unknown type, you'll get an unknown type was not declared in this scope, because diagnostics will be passed through the compilation error and will be just printed as an exception. So that's our break for the questions, if you have any.
So at this point, if there are no questions, it means everyone understands exactly how the underlying technology works based on
I will
Kris's
take
explanation.
it. So let's move on. Might be it's either scary or good. Let's assume it's good, and let's move on. That will give us more time to go through the examples. So having that in mind, we can implement some utilities on top of this basic JIT function, which we had already. So let's take a look into JIT compiles. You can imagine a function in which you pass something string-like, in that case, an expression, and you will return some form of expected, let's say std expected of some sort, which will return a compilation error in case if the compilation ain't be successful. So in that case, we already know how to do it. We have a try, we have a catch of the compilation error, we'll just propagate it to expected. And notice here, which is really important, is the fact that the expression, which was passed as a string-like thing, is being propagated to the angle bracket JIT. So we go from runtime to compile time. We JIT it. We JIT that expression. If that expression doesn't compile, then we'll just get a false. So imagine that. JIT compiles of the lambda works as expected. If you pass something which doesn't compile, that will just fail, and will just fail the assert. So we moved it from AOT to JIT time and go back to the AOT time in a sense with the assert as well, which is the runtime. But what about if you go further? imagine that we'll introduce this JIT assert, where we will pass the expression, which we'll try to execute. And notice here that we'll do the static assert in the JIT land. So we move from the runtime to compile time, and in this compile time world, which is the compile JIT land world in a sense, we can do the static assert, which is super exciting because then we can leverage all the performance out of it. So if you pass this expression, that will, won't trigger the static assert as expected, and this one on the other side, it will. So you can see that that's quite powerful way of dealing with the compilation things. Yet another thing which we can discuss is the fact that, as we mentioned with the clean, the REPL kind of it, you can imagine that the meta type, which is the string here, you can imagine the future that would be an abstract tree instead. And you can read about it in Andrew Sutton, the proposal about the reflection and dealing with stuff at compile time. So let's imagine a vector of this string, and we'll just push back int and double, which are, types, but in the string line. And we'll have some join function, which you can imagine, which will just join the first and last input iterators with the f function and add the separator at the end. And what is important here is the fact that we can leverage the runtime to compile time, but just using C++ manipulation of the meta, which is the string in that case, and maybe AST in the future, which means that we can leverage all the C++ algorithms. And as you know, Ben is an algorithm wizard here, so we can do everything we want with C++. Normal C++, we can use ranges and just produce a string version of something, and then by JIT moving to the compile time land with it, as this example, just to produce a tuple out of the vector, and then do the things at compile time in the JIT land, which is super exciting. However, the strings has also negatives, and you probably have heard of SQL injection. SQL injection is a popular attack in which you leverage the security breach in which users do not protect themselves from having a proper checks for names, for example. So if you pass the name and you end the quote, and after that you do or true and a comment, you can imagine that the SQL query, which will be propagated from the form, will look something like that, where the name will be empty or true, and after that we'll just leverage the comment, and that will be a valid SQL, which will always allow us to log in. Well, that's exciting, right? What about CVP injection? Have you heard of that? That's a concept which actually may happen with JITing if you're not careful. So imagine that case. You have a main, you JIT a cout, and get the user from the environment variable. Well, normal use case, right? You can imagine something like that. What if you pass John? Well, we'll get the John. What if we'll actually end the quote, do the system, remove the whole file, remove everything you have on your disk, and after the end the quote, well, that will be a valid C++, which is important because this code has to compile. And what it will produce, it will actually print nothing. Then it will remove everything you have on the disk. And after that, we'll just have this quote, which will do nothing just to compile it. So yeah, strings have benefits, but also they have negatives. You can also imagine that being a part of the compilation time. If you have embed stuff, you can get crazy here. So yeah, there are worries which you have to consider with CPP as well. And if you want to dig into more details, please take a look into last year Hal Finkel talk about how it works in details.
So I think perhaps at this point we can address a few questions that people put in. The first question is, what's the runtime overhead? So this is the way I've been thinking about this, at least in the use cases we have, is as a there is some. I mean, the runtime overhead is the overhead of compiling C++ at runtime, and so there is, as you would expect, some overhead. This isn't yet an invisible technology that can just take code and move it into magical JIT land seamlessly, but rather I'm thinking of it as a installation time or deployment time or configuration time step, which your users can apply, or which your internal users or yourself can apply. So there's some runtime overhead for sure, but you got to weigh that again, the total cost of compilation plus runtime. Another question: can you JIT within the JIT? Kris,
I
do you
can
want to
take
take this
that one. Sure. So yes, potentially you could do that. However, the current implementation doesn't allow you to do that, but you can go meta here. As you can imagine, there's nothing stopping from doing that. You can JIT even a different type of code, like you can JIT Python and after that JIT C++ if you really want. But the proposal itself doesn't allow that at the moment. And the follow-up is, do you have access to the global variables? Yes, you have access to everything in the host as well.
Right. Everything that the host program, the ahead of time compiled program exposes, types, variables, you have access to in the JITted code, in the environment that's JITted. And then the last question we had was, is it possible to sandbox the JIT? So Kris showed some SQL injection-like attack. We'll talk a bit more about that later on. I think there are some things we can do, but ultimately you're asking, if you're shipping this to users, and with internal users, you can expect them not to attack. But if you're shipping this to users, ultimately you are allowing them to run C++ alongside yours. And so I think any kind of mitigation is difficult at the source language level, at least. We had another question just come in. How big were the C++ programs we've tried while working on this functionality? We've tried injecting some pretty meaty stuff, and we'll come to that again in a little while as we get more into the examples. So let's move on. Another example here. So we talked about Cling. Using the JIT technology, it's fairly easy to set up a driver program to use C++ as a scripting language. And it looks something like this. So here we have a function which will just take the contents of a file. That's passed in argv1. We ignore the first line of the file because that's going to be the hash bang line. And we return the string of the rest of the file. And then we take that file contents minus the hash bang line, and we put them in a Lambda, and we JIT it and execute it. And that means that whatever you put in this file, here's a notional scripted file, and the first line is a hash bang, which tells it to use our C++ JIT program to run it. And then we run it on the command line, and it says hello world. So there we have a sort of very simple C++ as a scripting language using JIT. Of course, as Kris said, we still have the issue of what to do about includes here. The file contents go inside a Lambda, so we can't actually put a hash include in our script. And so maybe modules come to the rescue. Maybe we import the whole of the STL as one module. Precompiled headers can be used for a similar effect. But there is fundamentally a sort of an issue of what to do about includes, which we'll perhaps get to later as well. Another thing we can do is mix compile time and runtime. So we've seen some of this already, but here's another example. Here we have a sort function, and it takes some template parameters, some non-type template parameters, and some runtime parameters. And notice we're not JITting this yet. This is just a function which puts all of its parameters, all of its arguments together, both the compile time and the runtime, sorts them, and then makes them into a string, which is going to be the array of sorted values. And again, we're using the join function we talked about earlier. So now this kind of thing shows how we can have some. The way I think about this is you've got some configuration which is baked in ahead of time, and some configuration which is provided at this configuration time, at this deploy time, by your users. And so you can mix it together and do arbitrary things with it. In this case, the example is sorting it. Note that the sort function, as Kris said earlier, it's just plain C++. It's not const expr. All of C++ is available to use. And then here is another JIT use case I think Kris is going to explain.
Okay, thank you, Ben. So let's try to move on to maybe some more real world example how JIT can be used to leverage the performance and user feedback as well, because both of them are really important and both of them can be leveraged by using JIT. So you can imagine a function and the whole loop of it being something like that. So when we, whilst we have the input, and the input may come from different sources. Let's say if you have the REPL kind of input from the user, so you can imagine a researcher, physicist trying to, like a cling that add something to the program whilst working on it, or using an external data which may come from a file, TCP, UDP socket, without the UI or without any input from the user. So as long as we will have this input, we'll process it, and we'll do an additional step here, which will be just to collect that data in order to leverage it in the further future processing. So that's just additional step. And then, in case if you have an explicit trigger from the user, that would be the REPL case, or the collected data provides some kind of benefit, and you can argue here what the benefit is. You can use AI, I guess, or anything like that to verify when to actually the data which you get at runtime gives you any benefit, so that you can leverage it and promote the runtime data to the compile time data. And that's the main thing which is about JITting. So you have the runtime data which you collected, for example, the values and everything from the user, and after that you JIT, and you see the strings here being promoted to the types, and this way we can leverage the performance of JITting, because we'll be in the JIT land, which will have types, and will be the compile time version of it. Optionally, which is a super exciting feature in my opinion, is the fact that since we JITted something, we have the IR, intermediate representation, the binary, basically assembly, everything already there. It's in the Clang compiler, which is part of our application. So we can actually just save it for free. There's nothing which we have to do in order to not to save it, for example, if you want it. So that will allow us to produce a very optimized binaries which can be leveraged in the future without all this loop. So imagine that the researchers have finished some experiment and they just want to save a binary and release that one, or you find out with the AI that, oh my gosh, that's the thing. Let me just produce a binary for that so that they can use it later. So let's move on to show how we can actually do that with the few examples of dispatching, compile time dispatching and runtime dispatching. It's very often the case that we want to dispatch something, and the message flow isn't, most of the applications kind of leverage that part. So I feel like that would be a good example to show. So let's imagine that we have handlers which are called a foo and bar, and just print foo and bar based on the event if they're on call. And then we have three different types of events: E1, E2, and then E3. And that's the exciting part. We have the mappings, which can be extended at runtime, but let's start with another map, which is also a runtime version of it. we have E1, which is the handler, and foo, which is the event, and we'll go to the foo, which will be the handler, and add the same for the E2 and bar. And after that, you can imagine we can insert new things using REPL kind of thing, or when the data comes and you decided to do things and collect that data, we can extend that map. So if we have this mapping, we can create a dispatcher, and we can actually create a compile time dispatcher here. If you're familiar with Boost MP11, you'll be probably happy to see that. If you're not, I really encourage you, because it's a great library and it gives us a lot of performance out of the box. So you can imagine here that we produce a compile time map here from the runtime map. So we had another map, which is the mappings. We leverage this join function again. We get the event and the handler and produce a pair list, type list kind of thing, of pairs of event and a handler. And after that, I noticed that that wasn't a JIT function. It was just a normal function producing those strings, as Ben pointed out before. And after that, we have a dispatch, which is a clang JIT function. So the dispatcher will come from that string, and an event will come from the host. And what we'll do here, we'll just map find, which will return a handler for a given event, or void otherwise, and then just call on with given an event. I hope that makes sense. So what will happen when we call dispatch? So make dispatcher will produce this compile time mapping, and then the E1, which will be the event, which will try to find the mapping for. If you call it with E1, our mapping will say that's foo, and we'll print and we'll call on the handler, which will print the foo. And what will be the assembly? That's the performant part of it. It will actually be just the move to the move foo into the register and call the puts function. That's all. That's all which has to be done. So it's like super efficient. Well, can't be more. Cannot be even more efficient, right? What about E2? It will call the bar, as expected. So that's a way of getting compile time dispatch using the runtime information from the JIT when you're ready for it. What about if you call E3? Well, this map find won't be able to call it, to find it, and therefore will return a void, and we'll get this runtime compilation error. So like just in time compilation error, because it has no member. So that's where you have to be careful about as well, which you can get the compilation errors actually at runtime, not ahead of time. You can also call it with unknown event, and that will be a compilation error. That won't be a runtime compilation error in a sense, because the E4 is not known from the host. So, okay, but compile time dispatch is not always possible. Sometimes the input data is totally runtime. You can imagine the socket, you don't know what it is, you have just some definition of the protocol, you need to parse it or whatever. So let's try to make that happen with the runtime dispatch. So for the simplification, we won't use type traits or anything like that. Let's say we have just events with IDs, and these runtime IDs will be corresponding to those events. Then we'll just make dispatcher as before, but instead of producing the type list, we'll just produce a switch. We can actually generate the switch statement within the Lambda, which will take the ID, runtime ID, and in default case we'll assert, and in other cases we'll just do the case on the ID and call the handler on. You see the string manipulation here just to produce the switch code correctly, but the final result will be that the case of the handler, which are provided by the mapping, which are the another map, and we'll call it with the event, and it will just break. What is also kind of interesting is the fact that we can leverage like C++ tuning attributes here, like likely, unlikely, based on the runtime data. So that might be exciting to, kind of a PGO, profile guided optimization at runtime, and we'll leverage those attributes to speed up things on top of that. So I hope that makes sense. So what about if you have this dispatch function, which will take the lambda and we'll call it with the runtime ID. So notice here that the ID is being passed from the outside as an int. If you call it with 1, we'll get full. If you call it with that 2, we'll get bar as before, as expected. If you call it with 0, we'll get the assertion. That's the default case. Nothing really special. It works as expected, produce the switch case at JIT time. So moving on. So that was kind of exciting. We moved to JIT time and leverage the runtime information to make it much faster. But I mentioned that before, that what is super exciting is the fact that we already have all this compiled function in the memory, so we can actually leverage it and save it. So let's imagine that the JIT attribute for our dispatch function will have these additional flags, because we would like to, for example, make it as fast as possible. We'll do 03 or 09. If you listen to the keynote, with debug, and we'll just try to produce the intermediate representation, which is IR here, because we're using Clang, so it will be in the Clang terms. By default, the flags will be propagated from the host, so maybe host wasn't built with the debug because we didn't get an assert here. And the dispatch function will takes an ID. And notice here that the mangled version of that function won't take any templates. So the Clang JIT will remove the template part of it, because it will be moved from the template to the IR. So everything will be inlined in the IR. So we don't need the types for the templates anymore. And therefore we can easily just remove them from the mangled name and just call the dispatch. So if you dispatch with the mappings and 1, that will produce full as before, but it also will produce this intermediate representation file on the disk. We can also take the pointer to that function, and that will produce the IR information without really dealing with with running it. So imagine that we have a main function which just kind of extend that function, just a simple dispatch with the int. As I pointed out just a second ago, we don't need to pass the templates anymore, because the mangled name was removed by the Clang JIT attribute when we saved it. So it's just a void dispatch and int. And then we can leverage the command line argument to illustrate that we can take the runtime value of the first argument. So you can imagine our loop that would be somewhere where we were JITing. Then we'll use LLVM static compiler to produce a binary out of this IR, which takes basically no time. It's a very simple one-to-one translation. And then we'll compile it with our main. And notice here that we don't have to pass the JIT flag anymore. That will produce the optimized version of that binary, which will be just 1 megabyte, because there is no compiler included into it. And you can find this dispatch symbol in the list of symbols from the object files as well. So what will happen if you dispatch 1, we'll get full. If you dispatch 2, we'll get bar. If you dispatch 0, nothing will happen, because that was an assertion, and assertion was removed by the debug stuff. And the produced assembly will be very optimized switch case, basically, with a few jumps and few comparisons as switch would do. So there is nothing related to the unordered map or anything which host had, and it wasn't really used by the fact when we JIT after the JITing in the JITing land. So in a sense, let me rephrase that. Everything which is here in the main, it's just a part of the JITed function, and everything was required by the JIT land in a sense, nothing else. So I hope that makes sense. And I hope that's exciting for you as much as for us.
So we have a few more questions. Someone said, because of the complexity of C++ that we see in the compiler size, do you think it's a better idea to JIT some simpler language? Presumably meaning a language with an LLVM backend. I'm not quite sure how that would work.
Potentially you could do that. You could JIT Python as well. You could do that.
Does this allow for something like lazy constant initialization?
I would believe that.
Yes, I think so.
I think that's a good description of what JITing is actually doing, because it is constant, lazy by default, in a sense, if you look at it like that.
Someone says, does JITting a function on the host side make it easier to reverse engineer it? I don't think it makes it easier or harder, because it's basically the same compiler on the host side as on the JIT side.
Yes, I agree.
Would you say that same thing, Kris? It's basically identical. It's C++ being compiled with the same compiler, maybe different flags. So
yeah, you can imagine all of crazy
meta
examples when you JIT a function with different flags, and after that, another function with different flags. Try to use that together. And there are like totally meta crazy examples which you can think of, which you will not get into.
Someone else says, is there a way to indicate when you're done with all JIT so that any overhead might be removed from the executable at that time? Well, it's more a case really that you can produce a JITted executable, as Kris showed, which no longer has the compiler inside it. If you still want to JIT, you still fundamentally need the compiler. But this production of a JITted executable is kind of this. It's not really runtime. It's not really compile time. It's more configuration time or deployment time, as I've mentioned, at least to me.
Right, and the beauty of it is the fact that you can promote things from runtime to compile time as much as you want. So it might be fully compile time if you know everything ahead of time for the JIT time, or you can just compile like 50% of it and everything else will be runtime. So you have all the power here.
Right. I think we're going to push on, and we'll take other questions at the end, perhaps. So I want to talk a bit about JITting's interplay with concepts, because this is where I think it really shines. So here we have a concept. I mean, it's not a particularly good concept. It's for exposition only. But this is saying it's a concept on an I/O type, and it's saying you are a readable I/O if you have an IO.read, if you have a read function which takes a byte character buffer, a byte pointer buffer, and a size t size, and you return a size t, and same as is one of the standard concepts with C++20. So given that concept on an IO type, here is a type that fulfills that concept, and here is a type that does not fulfill the concept. So, okay, that's just the concept 101. How does JIT play into this? Well, we can use JIT to check the concept at the point where we load the user code. And the nice thing here is it doesn't have to incur the full cost of optimized compilation. We can just, at the point where the user gives us their code, or when I say the user, of course, it's usually the colleague. At the point where the colleague tries to load the code into the JITting system, they get a nice error message. And that's good. So there's a concept shape hole in our library, and you're trying to JIT something which fills that concept shaped hole. That's the idea here. Of course, the question remains, how do we produce this well-formed string? I blithely put on the slide here this string and it contains the structure names of my readable I/O, but that structure name is something that's inside a string of C++ source code which the user's given us. So we don't want to be parsing out structure names and things like that. So we somehow have to figure that out if the user code is passed to us at runtime. So one way to do that is, as we've seen, to wrap it inside a Lambda. Now, we could require that our users wrap all their structures, that the types they're going to pass in inside Lambda in this way, and they know the name, so that's fine. And we'll decal type it and we'll get the type of the thing out. And this works. It's sort of onerous on our users. What we want them to write is this, where they just give us a type as they would normally give it, and they don't have to deal with the noise of the Lambda and the decal type. Now, what we can do to make that easier, perhaps, is allow them to do that and then create a Lambda which will basically do as if they had done that. So what we're doing here is creating a string of a Lambda, and the Lambda is going to return the decal type of a Lambda immediately invoked. And inside that Lambda, all we're going to do is a using declaration for the type that was passed in, and then return that type. And one of the assumptions here is that we can default construct it. Maybe there are ways that we could get around that assumption, but for the purposes of this talk, we're going to assume default construction. So this is a bit nicer for users. It does still have some limitations on what they can do. As we saw before, includes are an issue. Because ultimately, all of what the user writes is going inside a Lambda. So there are a couple of limitations. One is includes, we've mentioned, and we can sort of get around that with modules or precompiled headers or making the host environment available. It fits in with an idea of, users can JIT stuff that fits in with our concepts, but they can't necessarily bring stuff in from outside. That might be good. Or in the case where we want them to include a third-party library, we could allow them to control the linking flags or the compilation flags and introduce their own modules or precompiled headers. There's another limitation here, though, which is that our users can't write templates inside their types because it's going to be inside a Lambda, which means it's going to be a local class inside a function. And currently, templates cannot be declared inside of local classes. Of course, they can really, because we can have generic Lambdas, which are templates inside local classes. And this is a kind of workaround for that. It slightly complicates the user code and the calling code, but it is a workaround that works today. But there's some further workarounds in future that we might leverage. So we mentioned precompiled headers and modules, which might come into play if users want to include stuff. We've got the future possibility, maybe the far future possibility of AST snippet injections using the meta or the various meta proposals that exist. In the nearer future, I think we've got a better chance for templates in local classes, especially since we do have them already with generic Lambdas, so there should be relatively little implementation problem with that. In fact, there are 2 papers which I believe have been seen by the standards body and now perhaps have been merged into one that both propose this idea, allowing templates in local classes. So, to me, the 20-year game programmer, my head just thinks of JITting as a concept for modding things. Normally, you would ship your program, and if you're going to allow users to mod it, you'd embed some kind of scripting language in there, like Lua or Python, maybe. But if you're shipping a JIT-enabled application, then you get this modding in C++ at, as I say, at configuration time, at install time. Versioning becomes, I think, easier because you don't have an explicit versioning system. You have an implicit versioning system, which is to say, here's the concepts I want you to fulfill. Here's what you must do in order to compile. If you compile, you are the correct version. You don't have to manually version things so much. You don't have to deal with ABI issues and DLL versioning, if that's your plugin architecture. And Someone earlier asked about sandboxing. Like I say, ultimately, if we're asking users to run stuff on their machines, sort of non-hardware based sandboxing or non-hardware supported sandboxing is very difficult at the language level, but we can do a certain amount of sandboxing with the type system. So here's one idea I had for doing that. We'll have a privilege level tag, and whenever we JIT something, what we'll do is take the user code and we'll wrap it inside a very thin wrapper class, which is just going to tag it with this privilege level, maybe in this way. And then we will have appropriate constrained functions so that they can't be called with the user types. Now, this speaks to us calling things sort of accidentally. We could also use the type system more to dependency inject APIs, which the users are allowed to use, and sort of wall off the rest of the stuff. Ultimately, as I say, this is C++. You can always try to, take a pointer to something and cast it and then call it. So there's no complete protection here, but there is at least sort of lightweight fences that we can put up and make it easy for people to do the right thing and make it easy to use without trying to break it. The goal is to provide a nice API and JIT time errors rather than complete protection. You wouldn't be shipping a JIT application if you needed a lockdown application, basically. So, of course, once you've thought about users in this way, why wouldn't you just think about yourself in this way? JITting breaks down the walls of the compiler and linker for you, for your project team, if you're providing a library, for your application team. And you get all these benefits. You get incremental compilation on a running system. You get the ability to patch things with source code if you need to do that on an endpoint machine. And you get this programming with concepts. Like I say, you build in concept shape holes of types in your system, and you allow people to just JIT inject things that fulfill those concepts. You don't have to think ahead of time about all the weird and wonderful IO types that they might want to use. You provide an IO concept that can read and write maybe, and then if they've got some weird IO hardware that they can support, they get to JIT a type that fulfills that concept. Hey presto, their IO is supported. So we're pretty much at the end of the talk. I'll leave it to Kris to summarize a little bit.
Thank you, Ben. So let's just quickly summarize what we've been discussing here and what JITting allowed us and what we can actually do about it in the future. So we just explored the Clang JIT version of it, so we won't be talking about JITting in general if it goes to the cost and benefits. But there are definitely benefits and cost of using that functionality using the Clang JIT proposal. So the first benefit is the fact that we can, improve the runtime performance, because optimization based on the runtime data and available hardware are something which you cannot do ahead of time, but we can do it at the JIT time very often, and that's a huge benefit which will allow AI and other things to make things happen at runtime. The negative, as we pointed out, is the string version of it means that we have these security concerns and some other issues with it potentially. Compile time performance is yet another super cool thing about the Clang JIT version in comparison to, for example, Cling, because we have all these benefits from memorization of the templated functions. So that's pretty cool, and that sped up the compilation of JIT classes by far in comparison to generating code and try to compile it with the compiler under the hood, because we can skip a lot of phases and it's already memorized in most of the cases either way. We don't support compile time injection though, so it means that we cannot do the mixing part of it with the D. That would be awesome if we could do that. And having direct access to the host is a huge benefit, because we can access everything from the host, and that always benefit because we can pre-compile stuff ahead of time. And again, we can leverage STL algorithms for the meta programming with types, which is super cool and allows us just to sort the strings instead of trying to compile time sort types. So what about quickly just about the future? In the future, you can imagine that this attribute won't be part of that's at least what the proposal tried to say with the future revisions, that the attribute won't be part of the function, it will be just at the callee side. So that will be the runtime version. We can also have a const expr version, which will be either runtime or compile time, or we can have const eval version, which will be just the compile time version. As well as, we can always pass the types in all cases. So you can imagine that the future may bring us similar interface, but much nicer, much more powerful integration with the compile time. And the stringless solution, that kind of maybe brings it to the reflection proposal when the AST node might be leveraged. And here to reify, it's from Haskell, and I have to thank you, Ben, for that term, to understanding of that term. And Andrew Sutton also is using it right now. Probably heard Ben talking about it. It sometimes is taking something that is abstract and regard it as a material. So it's like something abstract moved to the real world in a sense. So you can see here that we produce a meta type integral constant out of the runtime value and make it concrete as a type, and after that we'll be able to just call it at compile time. So you can read about it in Andrew Sutton, compile time metaprogramming. And that will be it, I guess. I'll let Ben finish.
All right. Thanks. Thank you, everyone. Thanks, Kris. We do have a few questions left over. We're right at time, but we can take a couple of questions. The top question is, this all seems very similar to eval in JavaScript. That's something largely discouraged in modern JS. How is this different / more useful? Well, I think the simple answer for me is JavaScript is dynamically typed and doesn't have concepts. It's fundamentally different. Like you're not necessarily allowing free reign. You're saying you've got to produce something which is this shape and which fulfills this concept. And I think that part of it is really great.
And on top of that, I guess on top of that, we have all these benefits from runtime data being available for you to produce much, to promote it compile time. And as Ben pointed out, type safe compile time version of it. So I think that both of that gives us the leverage of being much more capable GTN environment than the JS is.
So another question was, do the proposals for reflection and code injection reduce or eliminate the need for compile time JIT? They can speak to some of the same things. I think in a sense, compile time JIT is a superset even of reflection, because if you have the ability to fully compile something in a running program, you have reflection. You can take code and manipulate it as strings or manipulate it as meta objects. So they do play together there. I think JIT is strictly more powerful when viewed in the right way there, when given the right access to the kind of tools that reflection is going to allow us to have. So we should probably just wrap up there then. I think. Thanks, everyone. There is a SIGJIT channel in the Slack where you can ask more questions if you need to. Thanks for coming to the talk, and have a great rest of conference.
Thank you.